Hi, chemistry students. This is your Unit 9 lesson on exothermic versus endothermic reactions. You likely have some guided notes, but if you don't, be sure you are writing down the important and key points of this lesson. So far, we've been talking a lot about something called conservation of mass in chemical reactions as we learn different patterns and how to predict products. However, may have noticed as you are carrying out chemical reactions in the lab that there are energy changes as well, that some reactions get very, very hot. And in fact, there are even some reactions that get colder as they proceed, and some reactions that won't proceed at all unless you put a Bunsen burner under them. So we're going to talk a little bit about those energy changes as an introduction in this lesson, which is the final one of our unit on formulas, reactions, and equations. So first of all, before we talk about energy changes, we do have to define a few terms. So we're going to define something called the system and the surroundings. So when you're talking about a chemical reaction, you generally start with a mixture of reactants. So the system is that mixture of reactants, and the surroundings is everything else. And we're going to reference whether the energy is going in or out, depending on whether you're talking about the system or the surroundings. So this is, we've talked about the law of conservation of mass, but there's also something called the law of conservation of energy, which says that in a chemical or physical process, energy is neither created nor destroyed. And again, there are nuclear reactions, and we're not talking about nuclear reactions. In nuclear reactions, a small amount of mass is converted into energy. We are talking about normal chemical or physical processes that happen in our world on a normal basis. So in that case, energy is just kind of shifted around. So let's start by talking about things that are exothermic. And I want you to look at the word exothermic and think of the word exit. Exit means that something leaves. If you go to the exit, you are leaving the room. And thermic just means heat. So if you sort of think of this system as being the room, then an exothermic process means that energy is moving from the system into the surroundings. And in this case, that means heat is released. A good example of that process is a physical process of the dissociation of calcium chloride in water. And if you start with solid calcium chloride and you put it into water and have it dissociate, as you are allowing it to dissociate, you will notice that if you feel the outside, like you have a bag of water and you put the calcium chloride in, or a test tube of water and you put the calcium chloride in, and you feel the outside of the bag of water where it's dissociating, it gets very, very warm. And that's because their energy that was within the system is now going into the surroundings. Think of the air, think of your hand as being the surroundings, and your hand gets warm because the system of the calcium chloride going into the surroundings is in that direction. The heat is going from the calcium chloride dissociating into your hand, which is the surroundings. Heat is exiting the system, exothermic. On the other hand, if you've ever used a chemical cold pack, like you've been out on the sideline and you've sprained your ankle or there's been a bruise, and your coach gets this package of stuff and shakes it, and then you hear a little snap, that's an endothermic process. What's in that chemical cold pack is something akin probably to ammonium chloride or ammonium nitrate. It's a solid. In there, what you're hearing him snap or what you're hearing him try to shake to break is a little vial of water, so that when the ammonium chloride goes into the water, it actually takes energy from the surroundings. It's literally sucking heat from your injured body part, or from if you feel it in your hands, it's getting colder. It's taking energy from the surroundings and bringing it into the system. Heat is actually required or absorbed in an endothermic process. And again, I like to look at the word endo and think enter. Heat is entering the system. Seems weird to think heat entering the system makes your hands cold, but think about it. It's literally, for the system to happen, it's pulling heat from your hands. The reaction vessel gets spontaneously colder in that particular endothermic process. So again, to sort of reiterate, when something is endothermic, heat is being drawn from the surroundings into the system. Now that's either going to be, practically speaking, the surroundings, your hands getting colder, or you're actually going to need to put a heat source under this, like a Bunsen burner, in order to get something to happen. It needs heat for it to happen. On the other hand, exothermic, which is a much more spontaneous kind of thing, you feel the system getting warmer because there's energy leaving the system and going into the surroundings. And the most practical way of thinking of that is that's your hands. We'll talk about what delta H here is in just a minute. So let's talk about phase changes, physical changes, exothermic and endothermic phase changes, because I think they're really good illustrations of what I mean by energy flowing into the system or energy coming out of the system. And the fact that exo and endo don't mean hot and cold necessarily. So an endothermic phase change, in which energy has to go into the system to happen, are melting and boiling. In other words, if I have water, let's just think about water, ice, steam. If I have water and I have it in as ice, H2O solid, in order to get it to melt into H2O liquid, I need to apply energy. I need to put it on a stovetop. I need to take it out of the freezer. Heat has to flow into the system. There's actually more energy in liquid water than there is in ice because I've had to put that energy in for it to become a liquid. So melting is an endothermic phase change. Energy has to go into the system. Boiling is also an endothermic phase change. How do I turn liquid water into steam, into the gas? Well, I have to put it on a stove and I have to put energy in, and energy has to flow into the liquid water in order for it to be a steam or H2O gas. So endothermic processes are where energy flows into the system. And again, just to remind you, what this means is these are what we're starting with. We're starting with a solid and we're putting energy into the system. What we have in the product here is a new system that has more energy in it. Okay. Exothermic phase changes. Energy must be removed or flow out of the system. In other words, it's sort of like cooling. In other words, if I want to get liquid water to freeze, I have to take energy out of the system. I have to slow those molecules down until they reach a point where they can crystallize. I have to take the energy out of the system. So before, there's a lot of energy in this system with the liquid water, and I cool it, I remove energy from the system, and afterwards that energy, and again, it's exiting. I always think of exothermic as exiting, and when you exit, you leave. So the last thing you do is you leave, and that's why energy is on the product side. Energy is on the reactant side because I'm adding it to the reactant. Energy is on the product side for an exothermic reaction because I'm taking it away. It's no longer part of the H2O system. It's separate. It's different. Condensing is the same way. How do you get a gas to condense to a liquid? You have to take energy out of this system of a liquid of gas, and you have a system that has less energy. The energy is exiting the system. All right, now let's think a little bit about what this means. We have to talk now about what happens in a chemical reaction, and we have to define two terms: bond breaking and bond forming. So bond breaking requires energy. In other words, if I am let's just think about, instead of just boiling or melting, we're actually doing a chemical reaction where we have to, remember model building. In order to, change H2O molecules in a model to O2 and H2 molecules in model building, you'd have to pull apart all the pieces and reassemble them. So any chemical reaction requires that you break some bonds and then you reform them in a different way. And you need to know that bond breaking requires energy and is therefore endothermic. You have to put energy into a system to break those bonds. However, because bond forming is allowing the system now to be stable again, bond forming actually releases energy and is exothermic. So any chemical reaction is a balance between how much energy you have to put in to break the bonds, which is always going to be endothermic, and how much energy you get back out because bond forming is exothermic and releases some amount of energy. Now, we call the energy that is in bonds and that we put in and out here potential energy or enthalpy. And I think because of that H in enthalpy, they usually represent it with the letter, the capital letter H. That is the energy or enthalpy that is in the bonds, that is stored in the bonds during a chemical reaction. So in chemical reactions, bonds store potential energy or enthalpy. It's measured in something called, not in temperature, but in something called joules or kilojoules or calories. A calorie is the English unit, joules and kilojoules is the metric unit. Just like inches is the English unit of length, and centimeters is the metric unit of length. Joules and kilojoules is the metric unit of measuring potential energy or enthalpy, and calories is the English unit. The energy stored by bonds in the reactants is never exactly the same as the energy stored in the bonds of the products. So you have to think of sort of the bonds, the energy in that system of the reactants and in that system of products as being little storage areas, and it's never quite the same. But as we know from way back, energy is conserved. So the amount of energy on the reactant side and the amount of energy on the product side, including whatever excess, has to equal. I'll show you what we mean. So we define something called the heat of reaction. That's going to tell us whether the overall reaction is exothermic or endothermic. Remember, every reaction requires bond breaking and bond forming. And there's a balance. Does it take more energy to break the bonds, or more energy released to form the bonds? And this thing called delta, this sign delta, means the change. So the change in the enthalpy, which is known as the heat of the reaction, whether the reaction is going to get warmer or colder, for example, is the enthalpy stored in the products minus the enthalpy stored in the reactants. That's called the change in enthalpy, or the heat of reaction. So this is really, put a big star in your notes about this. Pause this, think about this. These are called potential energy diagrams. And this is the thing that we really want, now that we've gone through all of this background, that we really want to try to understand. So this is an endothermic potential energy diagram in which the overall system gains energy, gains potential energy, gains enthalpy. I always like to use the analogy of you having graduated from college, and you are the system and you are the reactants. And initially, when you graduate from college or from high school, you may need to move back home or stay at home with your parents. You have a certain amount of savings of energy stored in your system. You are the reactants. You're ready to go. And in this particular potential energy diagram, those reactants are storing about 100 kilojoules of energy. Now, happily, if you get a college degree or some post-high school training, you gain energy, you gain money, okay? And you break some bonds to get away from home. This right here, this amount, from 100 to 400 is the amount of energy you gained by getting a job. This is the amount of energy that is put into the reactants in order to get to the products. Here's your transition point, all right? And you end up moving into your own apartment. And when you move into your own apartment, you've got more money, you're gonna gain energy. And you see overall, at the end, from the reactants to the products, your gain in energy is 100, from 300 to 100, you have a positive 200. You have gained 200 in potential energy. And when you gained employment, when this system it adds 200, it ultimately gains products 200. So for an endothermic reaction, the energy stored in the products is greater than the energy in the reactant. So in other words, you have 100, you go up to 300. All right, so you have added that 100 and that 300, and now you have 300 stored as a product. It's an endothermic reaction. Your reactants have less energy than your products. Okay, you've gotten your job, you've now moved into a bigger space that allows you, the bonds of the products allow you to have more energy stored. Okay, so that's an endothermic system. Now, what about, an endothermic diagram essentially shows you that if here are your reactants, and they had stored in them about 100, you add your 200 and you get your products. Okay, so the products have more space. So if the energy stored in the products is greater than the energy stored in the reactants, then delta H is positive. The reaction is endothermic, and the energy term will be on the reactant side. In order to get to the products, we had to add energy to the reactants. So in other words, the energy in the reactants plus the energy we put into the system gives us the energy of the products. If we go back, you can kind of see that. Here's the energy of the reactants. We had to put, here's our delta H. That's the energy we had to put into the system in order to get to the products. And then the products have that much in it. All right. So in class, we're going to look at a particular YouTube video. And if you're in class, otherwise you can look at the slides and see this video. Okay, now let's talk about exothermic. This is where the system loses energy. This is where maybe you are gainfully employed and you decide, unfortunately you are laid off from work. So your input of money goes way down. Your input of energy goes way down. That big fancy apartment that you were able to buy when you were gaining energy now is not affordable. You have to move back home. You have to lose that energy. So in an exothermic system, the reactants that had all that energy from the job are going to lose some energy, okay, and have to go back to the products where you don't have as much energy or enthalpy. So for an exothermic reaction, the energy stored in the product is less than the energy stored in the reactants. And you can see it's exactly the opposite. So in other words, the products plus the energy you lost would equal the reactants. The whole overall system loses. You can see energy is being lost from the system. You've got negative energy now. Your delta H is going to be negative. So again, the idea is you had a lot of energy stored initially. When you lost that energy, you lost that job, you had to move to someplace smaller. You had to get rid of that energy. It's on the product side. It's exiting the system. Therefore, if the energy of the reactants is greater than the energy of the products, delta H is negative. The reaction is exothermic, and the energy term must be on the product side to balance the equation. In other words, the energy of the reactant has to equal the energy of the product plus the energy that you lost in an exothermic diagram. And again, I'm going to show you a video, and you can see in class, or you can go to this PowerPoint and look at the embedded videos. Okay. Now, there's one other thing you might have seen on those diagrams, something called the activation energy. That's the energy required to break the bonds in the first place. Remember, I told you bond breaking required energy to start the chemical reaction. You got to break the bonds. Before I can change the water models into hydrogen and oxygen models, I have to actually pull apart the models. So that's the energy that you have to put in to break the bonds. Now, in between me getting from the water models to the hydrogen and oxygen molecules, I've got this mess. I haven't quite, I've taken them apart, but I haven't put them back together. That's a transition state called the activated complex. An activating complex is the transition state molecule with some bonds partially broken and other bonds partially formed. I got a little illustration of this. So in other words, here's a reaction. If we're taking N2 to O2 and we're going to make two nitrogen monoxides, how do we get from that N2 molecule to that O2 molecule? Well, we have the two nitrogen monoxides. Well, we have to go through this transition. We have to break all the bonds, all the triple and double bonds here, and that takes energy. That's our activation energy. For a moment, we're in this state of higher energy where all the nitrogen, all the oxygen is broken. It's an intermediate. And then we're going to reform some bonds. We're going to reform the nitrogen and the oxygen so we can get two nitrogen monoxides. That is bond forming. That releases energy. And you can see the downside of what I like to call this sort of roller coaster potential energy diagram. So we have this bond breaking, this bond forming. The overall net is right here. Okay, this is an endothermic reaction. Overall, bond breaking takes more energy than the amount that's released from bond forming. So overall, this system is going to be, this transition, this chemical reaction is going to be endothermic. And finally, we're going to talk about this thing called what is a catalyst. A catalyst is a substance that does not change in a reaction, but lowers the activation energy of the reaction and speeds up the rate. So I sort of want to think of as a catalyst as being your friends, okay? So maybe you had a lot, like think about if you are somebody who lost their job, lost all your energy, and you have to move from someplace that stores a lot of energy to someplace that stores a lot less energy. Think of activation energy as being friends that help you move from your big apartment back down to your parents' basement. It makes it easier. Activation catalyst, what it does is it makes bond breaking. It makes the move from your big apartment with all your stuff easier, like friends would make it easier. So it makes it a lot easier to get to the end of the reaction. So a catalyst will lower the activation energy. Without your friends, it would take a lot of energy to move your couch from your big old apartment that you had when you had the job to your parents' basement or to the storage room where you're storing it until you get another job. Now, the beginning and end is still the same, but it's a lot easier if you have friends. And think about the activation energy as being your friends. So again, for example, you might have an exothermic reaction, and you're always going to go from the decomposition of hydrogen peroxide to water and oxygen gas like we did in the reactions to equations lab. Might even get a little hotter, but it's going to go a lot faster, as you saw when we added a catalyst. And that is your lesson on exothermic and endothermic reactions.